Log on, tune in, find out. Another good idea from Cambridge.
The organizers to arranging this workshop. It is very helpful, at least for me. And I will talk on design issues for transform both side nonlinear mixed effect models when you have some information about covariates, and this is an ongoing joint work with Basha and Kuresh Yodim and Stephen Gilmore. And this is my outline of the talk. At the beginning I will tell about the experiments which we are interested in, and this experiment is a part of the drug development process. I just want to mention in which stage these experiments are conducted, and then I will give a description of such similar experiments, real experiments, and then I will talk about two models I have used. One is single enzyme model, another is multiple enzyme models, and then talk about design issues related to these two models, and I will finish with a conclusion. So, drug development process can be divided into three big steps. One is drug discovery, second one is preclinical development, third one is clinical trials. In first stage, drug discovery, the candidate drugs are discovered with the hope that this will have positive activity on the biological targets, those are related to the disease. These candidate drugs, also known as new chemical entities or NCE. In the second stage, the preclinical development stage, there are a number of in vitro experiments are conducted, and some animal experiments, animal model also used in preclinical development stage, and drugs first applied to human in the clinical trials. The experiments we are interested in is a part of preclinical development stage, where main goal is to examine the pharmacokinetic profile of the drug, candidate drug, which includes examining the absorption, distribution, metabolism or excretion properties of the drug. Among these, the metabolism studies are useful to evaluate potential drug-drug interaction and also to predict pharmacokinetic variability among the patients. So, drug-drug interaction is the key term here. So, pharmaceutical companies interested to identify whether the new drug has any possible new drug has any potential drug-drug interaction or not. So, when a new drug introduced to the body, the drug metabolism may increase or decrease either by induction or inhibition of the enzymes. So, if the new drug inhibits the enzyme activity of the body, which may be used by other drug, then introducing the other drug would cause the drug-drug interaction. So, in these studies, we only examine whether whether the candidate drug has the possibility of causing drug-drug interaction. So, we want to check whether the candidate drug has any association with some enzymes. It is well known that cytochrome P450 or CYP enzymes are most important for metabolism, because these enzymes are responsible for about 80% of the metabolism of commonly used drugs. And so our goal is to check the association between the candidate drug and these enzymes. And liver tissue contains most of these enzymes. So in the experiment, we will use human liver microsomes and the candidate drugs. The human liver microsomes can be bought from commercial laboratories, and these, for each human liver microsome, these activity values of different CYP enzymes are known. So when you get a liver HLM, so you know what is the activity value of different enzyme of this family. So if you have 6 enzymes, then for each HLM you know the activity values. And each of the experiment involves a sample of HLM and a specific substrate of the candidate drug. And from each experiment, we measure the rate of metabolism as the response. So we have a series of experiments with different HLM and different level of concentration. And for each HLM, we will have several experiments, and from those experiments, we measure the rate of metabolism, and we can easily make the relationship between the rate of metabolism and the concentration for each HLM using Michaelis-Menten model, Michaelis-Menten equation, which is shows here. This is the process. So in x-axis we have a concentration, y-axis is rate, and it has two parameter Vmax, which is maximal rate, and Km, which is the concentration at half Vmax. So this model is used to estimate the enzyme kinetic parameters, which are Vmax and Km, for each HLM. So what they do, what the pharmaceutical companies do, they do a correlation analysis between these enzyme kinetic parameters and the activity values for each of the enzymes. So though for that enzyme, this correlation is high, they say this enzyme is important for this drug. So you have, if you have 6 enzymes, so you have 6 correlation parameter, and you from the values of the correlation parameter, you can identify whether the drug is associated to any of the enzymes. Okay. So here is the example of the experiment. So in this experiment, we have 48 HLM and 9 concentration, and so in total, all possible, you can have 432 experiment, and this industry did 2 replication of this 432 experiments. So in total, 864 experiments there. So, and for each of the HLM, 6 enzyme activity are available. So we know 6 enzymes. So we want to see whether any of these 6 enzymes are associated with the substrate concentration. Yes.
Is it the same 6 enzymes on each of
Yes,
the
same 6 enzymes. So you have 48 by 6 some matrix. Okay. So we want to see whether any of these 6 enzymes has any important effect on substrate concentration or candidate drug. Okay. So this is one way to show represent graphically the design. So in x-axis I have log concentration, and y-axis I have log activity values, and these are 6 different enzymes. So you can think each of the point as at least one experiment as conducted with at this concentration and with one HLM which has these log activity values. Okay. So this is not like a design, but this is a kind of a representation of the design, and you can think about, you can see what's the range of the activity values. There is no HLM which has the activity value in this range. Okay. And this is the data. You can see the different HLM. We can have a we can fit Michaelis-Menten model, and we can calculate Vmax and Km values for each of these HLM, and then we will try to correlate with the activity values to see the importance of the enzyme. So next, what kind of model should we use? I just say briefly that we are interested in correlation, and we have 6 activity values which are basically covariate, right? So here we are trying to do a correlation or regression analysis. The covariate, the function of regression of Vmax on the covariate or regression of Km values on the covariates. And you can consider 2 types of model. One is single enzyme model. So if you know beforehand only one enzyme will be important, so you can use single enzyme model, defined single enzyme model. And if you have no information on this, you can try multiple enzyme model. And here you can see that there is a variation between HLM. So you have to capture the HLM to HLM variation in your model. And in design aspect, we can say design of experiments vocabulary, we can say each of the experiment is a kind of a experimental unit, right? So, and here we have 2 treatment factors. One is HLM, one is substrate concentration. One treatment factor is fixed substrate, and another one HLM is random. So we consider, so sorry for this is a messy slide, but here my model. So first the response y sub I rs. I indicates the run, experimental run. So in total I have n runs. So n means 864. Ith run correspond to the R level of concentration and S level of HLM. So this model and this lambda indicates the box cost transformation. We assume after transforming both sides of the model assumptions hold. So we check our with our data, and we found this is the best model. If we model the Vmax as a function of covariate, we did all other model too, k as a function of covariate, both as a function of covariate. At the end we found this is the best model for the data we have. So this is transform both side nonlinear mixed effect model, because we are transforming both side. Vx is a contains the random effect term, k does not contain random effect term, and we assume that Bs, this is normally distributed and error terms normally distributed. So our goal is to estimate the parameters of the model, which are theta naught, theta 1, sigma b, sigma and beta. So one can use usual maximum likelihood estimator for this case, but we use a slightly different approach. So here you have 2 kinds of parameters. One is transformation parameter, another is nonlinear regression model related parameters. So these 2 parameters are quite totally different things, right? The transformation parameter just identify at which scale you should measure the response. So to for using this fact, we can calculate the transformation parameter from this total treatment model, full treatment model. So this is just a mean of the response corresponding to the treatment R and S, right? Combination of R and S. So this is what Box and Cox describe in their paper. So we calculate lambda from this model, and this lambda we plug in our transform both side nonlinear mixed type model. Now it is not anymore a transform both side. This is just a nonlinear mixed type model because the lambda hat is just a data. So you can use just NLME package or some other package to fit this model, but to fitting the transform both side model, you need to write your own function in some way, right? So this approach has some advantages, like you can easily test the lack of fit, and we have discussed about this fitting and compared with that ML fitting in our paper, which is under revision. And for ML fitting, one can check this paper here. It describes how to use maximum likelihood method for fitting transform both side nonlinear mixed type model. So from this approach, from this estimation procedure, we get all the parameters estimate, and now we just apply this approach to our data we have. So these are the estimate of the parameters. So you can see from here, though since it is in different color, the enzyme 4 is important. You can see because you can see from these values, you can see that enzyme 4, the sigma b value is smaller for enzyme 4 compared to the other one. Why it is smaller? Because the covariate take care of some variation of donor to donor, HLM to HLM variation, the covariate, that activity of enzyme 4. So this covariate has more importance than other one. Other covariate does not make any impact on the substrate concentration. So from here, or if you can check whether this 0.744 value significance or not, you can see, you can find which specific enzyme are important for that substrate. Okay? So this is our result. So at the end, we can say enzyme 4 is important if you assume this model. And next, okay. So here just I'm showing what is the difference between a important enzyme and not important enzyme in this plot. So these dot are data, and this black solid line fitting by enzyme 1, and red solid line is fitting by enzyme 4. And since we have many activity values, in this fitting we use the median activity values, and this red dotted line, in this fitting we use third quartile of the activity value, and here first quartile of the activity values. So you can see if you change the activity value of enzyme 4, you can cover a big region space, whereas if you change the activity value for enzyme 1, you don't cover you just cover a small space. So enzyme is important means whether it covered a big space or not. Okay. And next thing is how to design. So if you know beforehand, if you want to design for only one enzyme, this is the way to do it. So I only want to design for one enzyme. I know this enzyme is good. I want to design for this enzyme. So so what is design problem here? Design problem is we have a number of HLM, and we know the range of concentration. So we want to pick a combination of HLM and the concentration a number of times. So I know beforehand how many run I want to do, right? So I know the number of experiments, then I want to just find out which combination should I take so that my estimates are efficient. And I already explained that we have two models. One is a treatment model, another is a nonlinear mixed effect model. So, the treatment model will contribute to the design criterion for lambda, for estimating lambda, and this one will contribute for other parameters. So, for treatment model, we write down our information matrix, and we use here kind of a DS optimality, and this is our design criterion for lambda, and this approach has discussed in Antony's paper in JSSB 1997. So, so we have one part of our design criterion, and the second part we can get from here. So, this is our nonlinear mixed effect model. So, we can write down the information matrix, and this is your criteria, and this design criteria for only these parameters. If we add lambda to this parameter set, then our design criteria could be just sum of these two. So, you can use a weighted sum if you want, but this is enough. And we want to find that set of R and S for which this design criteria is maximum. Okay. So, in this case I will use exact design. So, I want to find out which set of pairs give the maximum value of this criteria. Okay. So, sorry. So, this is a nonlinear problem, and we need some prior information about the parameter, and we are using the estimate we have got from our data as a prior. And this is design when we are interested only on 40 runs. So, you can see the design for this is designed for different enzymes. So, we obtain these designs separately. Okay. So, for different different enzymes. So, you can see that enzyme to enzyme the designs are different. For first enzyme, there are at the low concentration level, there are some point in the middle of the activity level, whereas in the fourth enzyme, at the low concentration level, the points at the low level of the activity values. And just I want to tell that the design depends on the enzyme. Okay. So, different enzymes design could be different, and if I just if I check the marginal, then we see that there are a big a good number of runs at the high level and good numbers run at the low level of the concentration, and in the around the middle there is some runs, but in the fourth enzyme we see these two are equal weight, whereas in other cases these are in different weight. And in other level, other scale, so if you check it in activity level, you can see these are quite different for different activities. And this is, since this is an ongoing work, we did not have designed for more than 40 runs for all the enzymes, but we have some designs for more runs for only for the fourth enzyme. So, this is with 30 runs. The green color shows the marginal on a concentration level, and the red shows marginal on the activity level. So, we have 40s, 50s, 60s, 70, 80, 90 run design, and you can see the designs are basically 3 points, here one, and the highest level of concentration. And at the highest level of concentration, you tried lot of HLM, whereas here you tried only HLM which has low concentration, low activity values. Here you try HLM which has high activity values. And now question is how good this design compared to the design the industry use, that is a saturated design kind of, say use all the points. So we did D efficiency, we calculate D efficiency, and we see like our 90-point designs, you need only around 3 replication of the 90-point design, that is 270 runs to get the same efficiency as their 860 runs. So if we get more point design like 100, 120 point design, it will show better result, I hope. Okay. So this is the situation when you know only one enzyme is important, but in the situation say you know we have 6 enzymes, one of the 6 could be important, not specifically one. Then this model, this design is not very good in that case. So at that case we need to change our design criteria. So here we know the one single enzyme model is important, but which one we don't know, one of those 6. So in that case we need to fit this model for all 6 enzymes, and this is our criterion. We just calculate the psi 1 as we defined before and take a sum over all enzymes. So this is our design criterion, and this is the design, and this design is quite different than what we got for single enzyme model. So here you can see there are some points here which are not there, and especially this one at that design we have many points here, but there is no points in this region. So for fourth enzyme we get many points in this region, and this design can be used for single enzyme model, and so we can make a comparison how less efficient this design is compared to the design we have previously obtained. Oh, sorry, this is, I will come later. So this is the table. It says that if there are 30 runs, so if you use the psi2 design for estimating single enzyme model, then you will lose about 10% efficiency. And you see this is more for enzyme 4. One thing is, if you can remember the prior values, the enzyme 4 values is little bit higher. This could be the reason, because it lose more efficiency here. And this marginal plot is similar to what we got for the single enzyme model. Yes.
Yeah, you can see the concentration at 4. You're putting so many points in there to pin down the Vmax.
Yes.
And then you center, so it'll be the theta 0 in your parameterization. And then the other ones are just trying to get a little bit around
yeah.
K.
And the next question is, say it could, if it is possible that you could have more than one enzyme in could be important for the substrate. So then single enzyme model are not useful anymore. In that case, we need to consider a multiple enzyme model. So this is just adding your covariate in the Vmax values, and in this case you have say 7 theta parameters, 1 beta parameters, and other parameters. So we do the same thing, and we can write down our criteria as we did before. We will consider the same treatment model and the nonlinear mixed effect model, and this is our criteria. This M2 is the information matrix obtained from here. And this design, I use these values as the prior values, which are the estimate of we obtained from the data. And this is our design. So you can see this design is quite different than the previously obtained design, because here here you have not a straight line, you have some fluctuation. Here you have some fluctuation, not on a single line, right? And I'm coming back here. You can see this indicates more. So you have more points in the middle than just the 1 point. Okay. So in this 3 situation, we will get 3 different kind of design. So activity values and the model is very sensitive for the design. Okay, and this also different, and you can see more points in the middle. And another thing I want to, this is not the complete table, but I want to say like how many HLM do you need? So suppose you have 100 HLM. Do you need 100 HLM for 40 runs or 50 runs? So this is saying like if you have a 30 run, you want to make 30 runs, then for enzyme 1 you need 24 HLM, whereas enzyme 4 you need only 18 HLM, because enzyme 4 the activity values contribute more about the variation, donor to donor variation, so you need less donor. Okay. And this phi 2, where you have several single enzyme model, you need 24, and psi 3 you need 27. And I just calculate for this design. So you can see we have in total around 48. Even in 90 runs you don't need 48 donor. So it's not like all the time you just add donor. You have to have consider the other values like activity values and of course the prior information, right? So I finished very 5 minutes early, I guess, and these are the conclusion. So what I want to say that activity value has importance in designing this setup, and the same efficiency you can obtain by smaller number of runs if you do good design. And another thing I want to say for future, future work, we did not use here the Hill's coefficient, which is very commonly used parameter in this model. So next time we will try to use Hill's coefficient in this setup. And we also want to check the sensitivity of the design. So not necessarily for this setup, parameter values, for different set of parameters with how design change. If we put same value of the same prior value for all the enzymes, how the design change, these kind of things we will check in future. Okay, I will stop here. Thanks.
I have a couple of suggestions.
Yes.
So number one, currently what you do, you have 2-stage estimations. So first you estimate lambda, then use lambda to estimate your parameters. Can't you do simultaneous estimation?
Yeah, we can do.
And simultaneous estimation would be more realistic, because when you do 2-stage estimation, you assume that lambda doesn't affect parameters. So your covariance matrix is block diagonal when you compute standard errors for the parameters. So you simply assume that lambda is fixed. It is not fixed. So it has some influence on the parameters. So this is my suggestion number one. Suggestion number two, go to your model where you have exponential on the top, right here. So you showed us that lambda is about 0.2.
0.28 is.
Yeah, to me it means that log transformation is a good one. So if you take log transformation of both sides,
Why it's a good one?
because it's close to 0.
No, I did not say 0.2 is significantly different than 0.
Yeah, I know, but just try.
Okay.
Take log transformation. And if you take log transformation of your model, look what happens to your random effects. Random effects becomes linear.
Oh, you are asking to taking log transformation one side?
Yes.
No. For nonlinear models, the parameter has some interpretation. If you take the log transformation, the interpretation will not interpret in that way, you have to take transformation on both sides.
No, both sides,
Okay.
both sides. So you have log y,
Yes.
right, and log of this ratio of exponential functions. So what happens that your random effects become linear, and it's much easier to estimate linear random effect than dealing with this very nonlinear problem.
I think we've tried that some long time ago, and actually when we looked at the residuals, they were pretty bad.
Because
Did you try what what I
Yeah,
said?
long
so
time
this
ago.
is the best, best fit of to the data. But you're right. That if you take log transform, that it will be simple.
Yeah, me
But that's a different issue. But for this problem, we need to use this model. So just we try to suggest the design for this specific model.
Would it make sense to consider different lambda parameters on both sides?
No,
You lose the
then
interpretability.
you interpretability. The scale will be different, right?
Cannot you assume that lambda is known from your prior experiment, and then you assume lambda is fixed, and then all your design will be very different, I think. I
Yes,
think
because that one part, that lambda phi t will not be there.
yes,
So you will have only this part, right?
yes,
So
and then I
this,
think
this
you have
part will
only
not
points
contribute.
at
But I'm assuming like you will check whether which lambda you should use in the analysis. So that's,
as a theoretical point of view, I understand, but on a practical point of view, I don't know. You have very rich data. You assume you estimate lambda of 0.99.
but for this treatment model, it's easy to fit lambda because you need only one replication at one treatment level, right? But for global things, you may not be that accurately estimate the lambda. So one advantage of this ANOVA method, I say.
But I'm not sure that that's a terribly powerful way of getting at lambda, because you're trying to estimate the particular, you're trying to estimate one of two responses based upon the average. Your
depends on-
TRS is based upon two observations in this case.
Yes.
Right? And so,
But in appropriate design, in our case, you can see there are many points, right? In 50, there are many points. So here it is 2 points here, right?
I'm worried about outliers pulling the average toward them. You know, if it would be more appropriate to be on the log scale, then you're going to end up with, you know, a value minus a little bit plus a lot. But when you start taking the average of those two, it's going to be pulled up. So I would be worried about
So number of replication.
representability of that average, because it's based on only 2 points.
I agree. You have to, lambda is important in this case, so you have to pay more attention how to estimate lambda. In a simultaneous approach, you maybe are, but apparently 2 observations are not sufficient.
But we had a simulation in our paper, and there is no difference between maximum likelihood, which is simultaneous estimation, and this one. And there is advantage of having this way, like especially the estimating the lack of fit. That is very important because the treatment model, this one is the most saturated model you can assume. So whether there is a lack of fit, you can take it from here very easily.
When you fit your transformed model to the data, then I believe the fit is probably very good. But have you also looked at the fitted model on the original scale? So back transforming is that still giving you the fit?
Why do you need that then? Because you are already getting the estimate, right? And it's a good fit. So why should I go back?
If it is easiest to interpret the model on the original scale.
No. The parameter interpretation will be the same, just the scale difference. So it doesn't matter.
You still have to look at the original observations because you assume they are normally distributed.
No, I'm assuming after transforming.
Yeah, you assume yes, after transformation. So you got lambda and you still need to look at epsilon I sub I hat to see whether they follow the normal
Yeah, we did that.
distribution because this is your assumption. So this is what you're saying, right?
No,
No. He said something.
you were saying after back transfer.
Yeah.
Okay.
When
fine.
it might be on a
this is
log
back
normal
transfer.
scale.
But
God knows.
We already checked the lambda because after this transformation, the epsilon normally distributed these things. Diagnostic, we did that, at least for this data set.
It's good to see how epsilon has behaved, what the histogram would be.
Yeah, if I knew I have more time, then I could have that slides.
But, I mean, it's absolutely routine to transform back, so it's not you know, so everybody transforms back at some stage in their life.
Yeah, but you can't necessarily check this. Where is it?
Here.
Yeah, very good. I see. You can't necessarily check the distributional assumptions on the back transform scale, which I think was the point, wasn't it?
That's a
It's
separate,
fine for predictions, but
that's a separate issue. Yeah.
Q plot may help. Q naught.
Yeah, of course, the question of whether you marginalize over lambda or whether you condition on lambda has a rich tradition.
Yeah.
There was the analysis of transformations and the analysis of transformations revisited, rebutted, and, you know, it continued on for a while. And, you know, I'm in the conditioning camp, but I'm surprised that you would go with the number like 289. Why not look at 2.5 or 3.3?
Yeah. So we discussed. I don't know.
This is
I won't
based on
ask,
prior
so-
information if you have the, with the database.
Yeah, that's a good 2.5. We could take that.
Yeah.
Yes.
Any other questions? All right, well then, we thank both speakers.